action.
Hi, my name is Joe Chavala. I'm a member of the UNF's Society of Automotive Engineers Formula Team. And today I'm going to talk to you about a dyno. A dyno is a device that's used to put an artificial load on an engine so that you can measure the torque and from that calculate the horsepower on the engine from a static position without actually having to put it on a track. Here we have our housings that we've cast. This is the flask that we use to cast it from. Due to the shape of the housing, where there's a bulk of the mass is in the center hub and the thinner outline reaches, we had some issues with coming up with a means of casting it. So we actually created and built a 3-part flask so that we could put parting lines, both one on either side of the housing and then one to get the feeder out. So when we put this together, the housing sits in there, and then initially the metal is poured in this manner with the feeder actually on the bottom. However, when it goes to cool, the feeder is supposed to supply metal to the part as it cools to accommodate the shrinkage that you get when the metal cools. So what we actually had to do was pour the metal this way, close the lid, and then flip the flask over so that when it cooled or solidified, it was actually sitting like this. So on our first attempt, as we were pouring it, we didn't have the basin cut out, the part where you pour it into it. We didn't have that deep enough, and so we were not able to get the flow fast enough into the mold to prevent it from freezing short of the goal. And so we have actually, this is what it's supposed to be, and this is what our first casting looks like. So on the second casting, we dug our pouring basin deeper, which allowed us to pour it faster. In addition, we put a vent then in position on that arm that allowed us to both to vent the air from the mold and also to see when the mold was full, and then we were able to flip the mold over. And so our second casting actually turned out rather well.
Cool.
So a couple of things in the calculations that we performed going into this, the idea was to put a feeder on there. The purpose of the feeder, again, is to feed metal into the part as it cools. So you want your feeder to cool last, and you want all the shrinkage to occur in your feeder, which
shows the shrinkage.
You can see this was supposed to be round with a slight taper to it, and you got a fair amount of the side that has collapsed. In addition, this should be straight across here, and this should be flat, and you can see that the shrinkage is actually pulled in from the feeder itself, which was exactly what we wanted it to do. Also, one other aspect that we saw, part of the problem we had with this first pouring, not sure how well you can see it in the video, but you can see how porous this surface is. And I think we can see it maybe a little better on this side. You can see how porous this is. In addition,
see if we can
this side over here is a good example.
Oh yeah, right there.
Also, if you can see it here, you can see where we've sanded this, where we've cut the feeder off. We can sand all these little dots in here. Those are all from air pockets. Now you can look at the difference from the second casting, and you can see the surface is much fewer imperfections from the air pockets, and there's much less air pockets in where we've cut the feeder off. That was because we both from the venting and from the deeper pouring basin, we were able to eliminate a lot of the air intrusion. And you can see that on the sprues from both castings. This was the first casting.
Which one? This one right here?
This one right here.
Okay.
And you can see where all this disruption in here was caused from the actual air.
You can see the ripples in it.
Right. That from the air being introduced as this was pouring down as the molten metal was being poured down the sprue, it was allowing air to come back up through it, and that's what happened here with all the pores in the part. It's caused from the air. Whereas on this one, you can see it's a very smooth first surface, and you don't have all the pores or the disruptions.
So how did you fix that? How did you prevent it from?
Well, two things. We added the vent on the arm to help air come out, but also by digging this deeper, the pouring basin deeper.
This part right here. Okay.
This part right here. Now think of that in reverse, and we have some pictures we'll post on the website as well. But this would have been a hole dug into the top of the sand mold. On the second one, it was quite a bit deeper, and so what we were able to do is actually fill it. When we filled the first one, because this wasn't as deep, and also we had no other means of knowing when the mold was full, we had to pour a little more conservatively. So even though it looked like the sprue was full as we were pouring it, it was basically pouring off over the edge as it went down. Whereas this one, we were actually able to submerge the entire section of the sprue as we were filling it. So that kept the air from being allowed to be infused into the well as it was being poured down the sprue. So that resulted in a much better part for our second casting.
Cool.
Okay.
Anything else you have to add, Joe?
We're actually hoping to do another casting this summer when we've got more time, and we'll see how that one goes. Got a couple of changes we're going to make, both in how we're intersecting the sprue. You can see on this diagram. On our initial casting, you can see we ran the runner across the bottom of our sprue and had this out here as a means of trying to cushion the impact as the fluid, the molten metal, ran down past, so it wasn't as much of an impact. On the next one, we'll be actually doing it tangent to our feeder so that it will dissipate the energy by running around the outside.
Interesting. Cool. Is that it?
That's all I got.
All right. Thanks for sharing, Joe.